My name is Conor Walsh and I'm a final year electronic and computer engineering student at the University of Limerick in Ireland. Today I will be speaking about research that has been done into automating the analysis and optimization of Data Plane Development Kit, or DPDK for short, applications. During this presentation, how a DPDK developer could automate the process of analysing and optimizing DPDK applications using pre-existing and newly developed tools will be explored. To demonstrate how these ideas can be practically implemented by developers, an open source project has been released as part of this work, which leverages these ideas and provides a generic analysis and optimization platform for use with DPDK applications. This project will be discussed later in this presentation. This research focuses on DPDK applications running on Intel architecture processors.
The Data Plane Development Kit, or DPDK for short, is a set of C libraries that seek to provide a simple, complete framework for fast packet processing in data plane applications. DPDK is becoming a very popular tool within telecommunications and networking companies, as these companies are increasingly working to virtualize their equipment from traditional big iron fixed function equipment onto more generic platforms. This process is known as Network Functions Virtualization, or NFV for short. When developing a DPDK application, developers have many configuration options at their disposal to configure and set up their DPDK applications. While it is very advantageous to have such granular control over your application, this can lead to applications that are misconfigured, which can in turn result in losses in efficiency and performance. Profiling changes to DPDK applications manually is a very time-consuming process which has great potential for automation. Automating this process would allow developers more time to spend developing their applications, rather than configuring DPDK and checking that these options have not affected performance or efficiency. A scripting language would suit this project quite well, as they are often used for automation tasks and as such have many libraries available to help with these tasks. As we can see in this figure, Python is a very popular scripting language among developers both on GitHub and in the Stack Overflow 2019 developer survey. Python is also already being used by the DPDK project to develop some of its tools and scripts. Therefore, Python was selected as the language of choice for this tool. This tool will be very feature-rich, but from a high level, the logic for the tool can be broken down into simple switch flow logic. Firstly, the tool will read in and validate the user-supplied configuration files that will be used to set up the tests. If any of these steps fail, the application will abort. If successful, the DPDK application being analysed will be started. Next, the measurement tools being used will be started. The tool will now allow the test to run for how long the user has specified. The tool must check that no processes have died during the test, or the test will be invalid. All test processes must be killed. The tool will analyse the data generated by the measurement tools. If optimization is enabled, then the tool will follow pretty much the same process as above, except it will modify and rebuild DPDK as part of the process. Once this is complete, the tool will generate reports of the analysis and serve them to the user. In this figure, we can see the suggested data flow for the tool. CSVs were chosen as the method for passing information between the external measurement tools and the analysis and optimization tool, as most Linux-based measurement tools have an option to run the tools in a headless mode and save the data to a CSV file, and the user can also interact with the raw data if needed as well. The user will pass configuration parameters to the tool using a CFG or INI file. A Unix socket is used to communicate with the DPDK application through the DPDK telemetry API. The reports will be available to the user over the web or in PDF and zip archive forms. The suggested platform layout for the tool can be seen in this figure. It shows an example platform configuration for a dual socket system, where the system is running dual thread DPDK application across sibling hyperthreads on one socket and is running a traffic generator, the tool, and the external measurement tools on another socket. This setup is recommended to ensure the statistics collection does not interfere with the tests being run.
The tool discussed in this presentation uses external measurements tools to collect its statistics. The advantage of using pre-existing measurement tools instead of building your own is that the companies and groups that supply these tools perform rigorous testing and validation on these tools to ensure their accuracy. This will allow us to have very accurate test results with minimal code effort. It is very important that all of the measurement tools that we select are out-of-band measurement tools that do not require code changes to the DPDK applications to collect statistics from them, as this will allow us to use this tool with any DPDK application without having to change its code. As part of this tool, Process Counter Monitor, or PCM for short, was used to measure statistics about the Intel CPU in the system. Intelligent Platform Management Interface Tools, or IPMI tools for short, were used to measure platform statistics. and the DPDK telemetry API was used to collect telemetry information from the application being analysed. All of these tools are out-of-band measurement tools. To automatically optimize DPDK applications without performing any code changes, the tool will perform analysis using the original DPDK setup and configuration that the developer has supplied to the tool. The tool will then change various DPDK configuration options. The DPDK configuration file has over 350 configuration options, all of which have various effects on performance and efficiency. Once that is done, the tool will rebuild DPDK and the DPDK application with the new configuration options. The tool will then rerun the analysis of the DPDK application and compare the results. Using this information, the tool will recommend to the user if they should adopt the new changes or not. Finally, the tool resets the configuration options and rebuilds DPDK and the DPDK application with its original configuration for the user's convenience. Only one optimization step has been implemented in the tool so far. This will serve as an example to developers. As other optimization steps are researched, they can be added to this tool. The optimization step used in this tool is based around memory buffer recycling in DPDK. The original research about this optimization step can be found at the link which is on screen now. In order to maintain brevity in this presentation, the implementation for this tool has been omitted. The full implementation can be seen in the open source project, which can be found at the link on screen.
We can now see the tool in action. It can be run simply by calling the Python script. First, the tool pulls in the user's configuration options and shows them in the terminal so that the user can validate them if necessary. Next, the DPDK application is allowed to start up and settle. Now the tool is running a 30-second analysis of the application. In this example, optimization is enabled and the tool has edited the DPDK configuration and is now rebuilding DPDK. We will rejoin this process when it is complete. Now the same settling and testing process is completed to compare the edited configuration with the original configuration. DPDK will be rebuilt and returned to its original settings. We will again rejoin after this is completed. Finally, the reports are generated and served to the user. All of the information collected in the test has been automatically compiled into a report for the user. The reports are available in HTML and PDF forms. A zip archive is also available, which contains all of the raw data from the tests as well as the reports. Full example reports are available as part of the open source project. The report scrolling on screen now is an example of a full analysis and optimization report produced by the tool. To test the implementation and validate the results being produced in the reports, parts of the reports were created by hand and then the same parts of the report were generated using the implemented tool in order to compare the results. Two different DPDK applications were used to validate the tool, and these applications were suitably different to test all of the different functions of the tool. It was found that the reports that were generated by hand matched the reports that were generated by the tool, which were automatically generated in a fraction of the time. This validates the tool for use in production environments.
The DPDK Optimization and Analysis Tool, or DOTE for short, is the tool that was developed as part of this work. DOTE has been open sourced and is available from GitHub under an MIT license. Therefore, the user does not have to implement these methods themselves, but can use DOTE to fulfill their DPDK optimization and analysis needs. However, as DOTE was intended to be a very generic platform which developers would build on top of and modify to serve their own needs, it is very useful to understand the concepts and methods used in DOTE to make DOTE fit your needs. The full DOTE package is available from the link on screen. From this work, it can be concluded that it is possible to automate most analysis and some optimization steps needed by DPDK developers using Python. This will result in massive time savings for DPDK developers as these operations no longer need to be completed by hand. When using this tool, the amount of time taken to generate a full analysis and optimization report from a DPDK application can be reduced from several hours to only a few minutes. This should result in a time saving of over 94%. The time saving will vary based on the test length and complexity. I would like to take this opportunity to thank my co-authors, Dr. Tom New with the Electronic Computer Engineering Department at the University of Limerick, Mike O'Hanlon with the Architecture and System Engineering Office of Intel's Network Platforms Group, and Brendan Ryan with Intel's Network Platforms Group. I would also like to thank the software engineers from the Cable Technologies and Data Plane Development Kit teams within the Network Platforms Group in Intel Shannon for their continued support during this research.
This work is partly supported by funding from the Science Foundation Ireland Centre LERO, the Irish Software Research Centre. The hardware for this work was provided on loan from the Network Platforms Group at Intel in Shannon, Ireland.